So guys, in this lecture we are going to study preparation of haloalkanes. We have discussed a number of methods of preparation of haloalkanes. One more method is preparation from alkenes. Now see, we have two types of alkenes over here. I will discuss two types of alkenes. One is called symmetric alkene. This is our symmetric alkene, and the other one is called asymmetric alkene or unsymmetric alkene. Now this is my carbon-carbon double bond. To this carbon-carbon double bond there is CH3 group attached, there is hydrogen attached, and we have two hydrogen atoms attached to this. Now this carbon is sp2 hybridized because the number of sigma bonds is 3. This is also sp2 hybridized. We call this carbon atom as sp2 hybridized carbon atom. Since the groups attached to this sp2 hybridized carbon atom are similar to the groups which are attached to this sp2 hybridized carbon atom, that's why it's called symmetrical alkene. Since the groups attached to this sp2 hybridized carbon are only hydrogen atoms, and to this there is one methyl group and hydrogen atom. Therefore, the groups attached to two sp2 hybridized carbon atoms are different. Therefore, it's called unsymmetric alkene. Unsymmetric alkene. Unsymmetric alkene. Now, to this symmetric alkene and unsymmetric alkene, from this alkene and this alkene we are going to prepare haloalkanes. We treat these alkenes with halogen acids. For example, we treat it with HCl. For example, we treat it with HCl. Now this reaction is an example of electrophilic addition reaction. We will see the mechanism of this reaction, how the reaction takes place, and what happens when we have a symmetric alkene and what happens when we have an unsymmetric alkene. Now take this symmetric alkene, CH2 double bond CH2. This is our symmetric alkene. To this symmetric alkene we are adding HCl. HCl means H positive and Cl negative. Now HCl ionizes to give H positive and Cl negative ions. H positive is our electrophile over here. This is electrophile. Electrophile. Now see, if this bond breaks, this is a pi bond, it's a weak bond. If this breaks, this bond can break towards this side, we can get negative charge over here, or it can break towards this side, we get negative charge over here. Since both the carbon atoms are symmetrical, therefore it does not matter to which side you are going to break the bond. Let us break the bond towards this side. If we break the bond towards this side, it becomes negatively charged, and negative charge then attacks this proton. Means I will show it like this. This pi bond breaks, it attacks this proton. Pi bond breaks towards this side, attacks proton. If the pi bond breaks towards this side, then this carbon becomes del positive. We get CH2 positive, single bond CH3, CH2 and H, that is CH3. Now in the next step what happens? This Cl negative attacks. Now in the next step this Cl negative attacks. Since carbocation is formed as an intermediate, this is slow step. Now slow step involves addition of positively charged species, that's addition of electrophile. This is an example of electrophilic addition reaction. Electrophilic addition reaction. This is an example of electrophilic addition reaction. Now in the next step, this chlorine attacks, we get CH2Cl, that's our haloalkane, and CH3. This is the haloalkane we get from this alkene. Now what happens when the alkene is unsymmetrical? When the alkene is unsymmetrical, then what happens? This is important. When alkene is unsymmetrical, to which side we are going to break this bond? Now take the alkene. If alkene is unsymmetrical, let's take it over here. Now if our alkene is unsymmetrical, this is CH3, CH double bond CH2. We treat it with H positive and Cl negative. Now first step of this reaction is addition of electrophile. Now I can break the bond towards this side. If I break it towards this side, this becomes positively charged. Or I can break the bond towards this side, then this becomes positive charge. Now this positively charged carbon is primary carbocation and this is secondary. Therefore what I am going to do, I will break the bond towards this side. Means this carbon becomes negatively charged and this negative charge abstracts H positive ion. I will show it in one step. Now this pi bond breaks, it abstracts H positive ion. We get CH3, single bond CH positive, single bond CH3. Now this is our 2-degree carbocation, a more stable carbocation. Now to this carbocation, next step is addition of chlorine negative. This chlorine negative ion substitutes over here. We get CH3, CH, single bond CH3. This is how we prepare haloalkanes from alkenes by treating them with halogen acids such as HCl. Now see this haloalkene, how can we predict the products directly without doing mechanism? Now see, let us take a compound CH3, single bond C, H2, single bond CH, double bond CH3 and CH3. Now see, in this case we are adding H positive and we are adding Cl negative. Now what happens in the first step? First step, addition of H positive. Now if I add H positive, I have to break this bond. To break this bond, I have to form carbocation. If I break this bond towards this side, I get positive charge over here. That's a secondary carbocation. Now if I break this bond towards this side, I get positive charge over here. That's a tertiary carbocation. A more stable carbocation is formed. Means there are two ways by which I can break this bond. There are two ways by which I can break this bond. This is my path A and this is my path B. Now path A, I am breaking this bond towards this side. This becomes negatively charged and it abstracts H positive ion. In path A, I am breaking the bond towards this side. Then I am getting this type of intermediate CH, CH2, CH. This hydrogen attacks over here. Single bond C positive, CH3 and CH3. Now in path B, I am breaking the bond towards this side. This is my path B. If I break bond towards this side, then this abstracts hydrogen atom and positive charge is created over here. I get CH3, CH2, CH, positive charge, single bond CH, CH3 and CH3. Now in the next step what happens? Attack of Cl minus, attack of Cl minus. Now Cl minus attacks over here, Cl minus attacks over here. I have to predict the major product. Then the product of the reaction will be CH2, CH2, C, CH3, CH3 and we have Cl over here. And in this case the product of the reaction will be CH3, CH2, CH, Cl, CH, CH3, CH3. Now what will be the product of the reaction? Whether this is the major product or this is major product. Which among these will be major product of the reaction? Major product of the reaction is that which is formed from more stable carbocation. Now this is formed from tertiary carbocation, this is formed from secondary carbocation. Therefore this is major product and this is minor product. This is formed, for example 80%, this will be formed 20%. Therefore we can generalize the rule over here. Addition of H positive, see, addition of H positive takes place on this carbon atom, not on this carbon atom. Means addition of hydrogen H positive takes on this carbon atom which is more rich in hydrogens. It has already one hydrogen atom. Next hydrogen gets attached to this carbon atom which bears hydrogen atoms, not to this which does not bear. Means first step, that's addition of H positive ion adds to that carbon atom which bears maximum number of hydrogen atoms, or it may not be always H positive, it may be any electrophile. Electrophile adds to that carbon atom across carbon-carbon double bond which bears maximum number of hydrogen atoms. Now see, in this case electrophile H positive, it may add to this, it may add to this, but it contains maximum hydrogen atoms, therefore electrophile adds to this. Now we can make a generalized rule over here. It's called Marconi-Koff's rule. Marconi-Koff's rule states that Marconi-Koff's rule. This rule states that in case of addition of electrophile to an unsymmetrical alkene, electrophile adds to, let me write it E positive, electrophile adds to that sp2 hybridized carbon, means that carbon which bears carbon-carbon double bond, sp2 hybridized carbon which possesses maximum number of hydrogen atoms, Means this carbon atom is rich in hydrogens, it becomes more rich. This is less in hydrogen atoms, it becomes less rich. Means this rule simply states that rich becomes richer. Rich becomes richer. Now we have already discussed this rule in class 11th. This is how you prepare haloalkanes from alkenes. Now we will see one problem of this and we'll predict the major product of the reaction. Now let us take the reaction is like this. CH3. Now see, let us take the reaction is like this, not like this. It is CH double bond CH2. Now see what happens. 1, 2, 3, 4. Addition of HCl will take place. Now first step involves addition of electrophile, that's H positive. Now to which carbon atom out of these H positive adds? To that carbon atom which is rich in hydrogen atoms. Now it has 2 hydrogen atoms. It is only 1 hydrogen atom. Therefore hydrogen will attack on this carbon atom and chlorine on this. We get the product. Without doing mechanism we are just getting product. This is very important. The questions are asked from this. Now hydrogen will be attached to this carbon atom. Why? Because it is rich in hydrogens. Rich becomes richer. Now this is CH3 and this is CHCl. Now let us take one more example. This is our cyclopropane ring. Now to this cyclopropane ring we have carbon and it is doubly bonded attached to carbon, and this carbon is attached to another cyclopropane ring. This carbon is attached to another cyclopropane ring. Now to this we are adding H positive Cl negative. Now addition takes place across carbon-carbon double bond. Now this carbon bears hydrogen atom and this does not bear. Which bears maximum hydrogen atoms? Hydrogen gets attached to this. Therefore hydrogen gets attached to this and chlorine gets attached to this. We get the answer. This is very simple trick. Now this is CH3. Cl gets attached to it and we have single bond, double bond breaks. We have CH2 single bond cyclopropane ring. This is the answer. This is how you have to solve the questions. Now there are 2 more methods of preparation of haloalkanes. 2 more methods of preparation. They are particularly useful for a particular type of haloalkane. One is known as our Finkelstein reaction. Finkelstein reaction. This is very important reaction for competitive exams. Finkelstein reaction. Now see, this is also known as halogen exchange reaction. Halogen exchange reaction. It's also known as halogen exchange reaction. Now see, in this reaction what we are using? We are exchanging halide, that is iodide. We are using sodium iodide as reagent, and we are using in this solvent we are using acetone. This is very important. You have to remember solvent of this reaction. That's very important. It has its applications in this reaction. Acetone is used as solvent. Now this method is particularly useful, particularly used for the formation of, for the preparation of iodoalkanes, for the preparation of iodoalkanes. Haloalkanes में iodoalkanes अगर आप बनाना चाहते हैं, this method is particularly useful. Now see how the reaction takes place. Now see, we have a compound Rx. This is our RCl, for example. This is our haloalkane. We bring about halogen exchange reaction, sodium iodide. Now exchange of halogen takes place. This is the halogen atom. This is halogen atom. They exchange positions. We get Ri plus we get NaCl. Now the reaction is carried out in acetone. Acetone is a non-polar covalent compound. Non-polar covalent compound. Now this is formed as PPT. Why a PPT is formed? Because sodium chloride being ionic does not get dissolved in acetone. Therefore PPT is formed. Now similarly we can carry out reaction with Br, NaI. It gives RBr plus we get NRI plus NaBr. This is also PPT in acetone. Now what are the applications of this point, where of this reaction, where the reaction becomes important? The reaction becomes important in this case if we have to prepare, for example, C2H5, we have C2H5Br, we are treating it with sodium iodide, we are preparing C2H5I plus we are getting NaBr as PPT, because we are taking the reaction in acetone. Solvent is acetone. Acetone is non-polar. It does not react. It does not ionize in acetone. Or we can prepare C2H5Cl plus sodium iodide. In acetone we get C2H5I plus we get NaCl. This is PPT in acetone. Now can we prepare this type of reaction? Can we exchange this C2H5I by treating it with NaBr or NaCl? Can we get the product of the reaction C2H5Br plus NaI? Does this reaction proceed? This reaction does not proceed. This is the crux of this reaction. This reaction does not proceed. Now this reaction cannot take place. Now why the reaction cannot take place? Let us see the results why this reaction does not happen. Now see, मैंने आपको पढ़ाया फजन्स रूल. फजन्स रूल बताता है स्मॉल कैटायन लार्ज एनायन. Smaller the cation, larger the anion, more is covalent character. More is covalent character. Now see, take these examples. We have, for example, what is formed? NaBr is formed, NaI is formed, NaCl is formed. Now cation is same in all the cases. Iodide ion is larger, therefore it has more covalent character. This is more covalent. Our solvent here is acetone. This is also covalent. Now like dissolves like, covalent compounds dissolve in covalent compounds. Therefore NaI dissolves in acetone. That's why a PPT is not formed. Or in other words we can say this forms bonds with the acetone and is not easily replaceable. That's why we cannot use this reaction. That's why this reaction is particularly used for the formation of alkyl iodides. This is about this reaction. Now one more reaction is, that is for the formation of alkyl fluorides. For the formation of, after that we will discuss reactions of haloarenes in the next lecture. One more reaction is it's called a Swartz reaction. One more reaction is, it's called Swartz reaction. Now this reaction is very important. It is used for the preparation of, mainly used for the preparation of alkyl fluorides. Alkyl fluorides. In this reaction, this is also halogen exchange reaction. In this reaction, we treat our haloalkane RCl or RBr. We treat it with reagents like AgF, Hg2Cl2, mercury chloride, or we can treat it with SbCl5 or SbF5, antimony pentafluoride, very strong acid. This is a very strong acid. It decides to give Sb3 plus Sb4 negative plus HF. Now see what happens. Exchange of halogen takes place. We get Rf plus AgCl. We get Rf plus AgBr. This is very important reaction only for the preparation of what? For the preparation of fluoroalkanes. Now these were the methods for the preparation of haloalkanes and haloarenes. Now in the next lecture we will study reaction mechanism of haloarenes. What type of reactions do haloarenes undergo and what not? Thanks for watching.